Hello, this is Austin William Edler, and this is my Physics 2211 Constant Velocity Lab. So, the purpose of this lab was to examine the difference between two graphs, the first being a real-world video we took of a cart moving down a frictionless air track, and we used the tracker application to track its motion. So that's the first graph, and the second one is from program motion, which we used Python to simulate an ideal object moving at a constant velocity. And what we're going to do is we're going to look at the key differences of the two graphs, the real world versus the programmed, and we're going to look into sources of error where the two graphs might differ from each other. So we are using a frictionless surface in this lab, but I put the quotes around it because the air track, while it does simulate a frictionless surface, it does have a coefficient of friction about 0.0033. So that force will still be present, so we'll have to take that into account. And for the digital model, we are using Python code. And just by the nature of code, it will be a perfect simulation of an object moving with no net force, no constant velocity. And so we're dealing with Newton's first and second law in this lab, which is we'll be seeing that the net force is 0 and that F equals ma. And we will also come to find at the end that real world forces such as gravity, friction, air drag will play a role in the difference in the graphs. So the basic physics principles of this, the system and surroundings. My system is the hand that pushed it, the car and the track, and the surroundings is the air for air resistance and the world around, like with gravity. And the equations that we're using, pretty simple equations. We just got that velocity final equals velocity initial because the net force is 0, and also F equals ma. So here's the first graph. This is the one done with the tracker app. You can see I used the clicker to track the center of mass at every position. And you can also notice how it's not at an exact interval every time because, human error with the mouse. Tried my best, but you can't always get it exactly at the center of mass every single frame. And then you can also see up here on the graph, it's not necessarily just a straight line. It kind of starts sloping downwards, so that'll start to foreshadow what we'll see later. And then on the glow script, it's just a perfect graph. Obviously, it was coded, so you can see it's just a straight line. Every time interval, it moves the same exact amount. And yeah, that's just what you get when you're using a computer that's simulating it directly. So here's the comparison. And you can obviously see the orange is the predicted, and by predicted I mean the computerized model, and the blue, I guess, is the observed. So that is the real world data. That's the one I got with the tracker, and you can see a huge difference, and it starts to kind of get more so at the end, and that's because the object is technically decelerating, so the velocity will decrease at a decreasing rate, and also just the slope is less. So the average velocity of the observed is less than the predicted just because of these real world forces, while the predicted is just essentially in a vacuum with no other force. It's a simulated model. So some what ifs. We can think, what if a force was continued to be applied? Like what if the hand kept moving? Then there would be acceleration on the cart and the graph would be more concave up than just a straight line. And we can also think, what if the surface had more friction than, like a regular table, not an air track that we went out and bought? Then the cart would slow a lot quicker. It would decelerate more rapidly, and the deceleration would be more evident, like a slope down, like concave down, than just, or not a slope down, but it would be going up, but it would be concave down just because of the excess friction. So some sources of error, like I said earlier, the frame movement on the tracker, like just a human doing it with a mouse, unless zooming in and enhancing the image, you can't. There's a little bit of leeway with the center of mass and where you're clicking. And the other source of error, like I've been saying, there's not truly negligible friction. It's like, less than a hundredth, but there is a coefficient of friction, so that will cause the cart to slow down a little bit. If it went on forever, it would eventually come to a stop. And there could also be air resistance. I said could, but there is always air resistance. It's just probably pretty small because the surface area of the cart is small and we are inside. It's not like there's wind. But yeah, so there's air resistance and friction. So what does it mean? The net force is 0 because technically there's no forces on it after the force is applied initially. There's nothing pushing it in the positive x direction, and there's a slight force in the negative x direction. But either way, this lab is simulating constant velocity. Thank you very much.